Hello and welcome to Math Zone African Motives. Today we're diving into a past paper question covering a range of calculus topics. We'll be tackling this comprehensive question, breaking it down piece by piece. By the end of this tutorial, you will be able to find turning points of a cubic function, graph a polynomial, use Newton's method for approximations, solve a classic optimization problem, and finally, calculate a related rate. Let's get started with the first part. Our first task is to analyze the function given in question 3.1. The function is f of x equals x cubed minus 2x plus 3. In the first part, 3.1.1, we are asked to determine the coordinates of its turning points. So how do we find turning points? A turning point occurs where the slope of the function is exactly 0. To find the slope, we need the first derivative of the function. This derivative, f prime of x, tells us the gradient at any point x. So our strategy is to differentiate f of x and then set that derivative equal to 0 to find the x coordinates of the turning points. The formula for the derivative of a power function is the power rule. If we have x raised to the power n, its derivative is n times x raised to the power n mod 1. We will apply this rule term by term to our function. Now, let's find the derivative of our function. We'll write down our function again. X equals x cubed minus 2x plus 3. We differentiate this term by term using the power rule. For the first term, x cubed, the power is 3. So we bring the 3 down and subtract 1 from the power, which gives us 3 times x squared. For the second term, negative 2x, the power of x is 1. We bring the 1 down, multiply by 2, and subtract 1 from the power, making it x to the power 0. Any number to the power 0 is 1, so the derivative of negative 2x is negative 2. And for the constant term positive 3, the derivative is always 0. The slope of a horizontal line is 0, and a constant represents a horizontal line. Putting it all together, the first derivative of our function is 3x squared minus 2. This is the expression for the slope at any point x on our graph. We have the derivative. Now we need to find where the slope is 0. We set our derivative, 3x squared minus 2, equal to 0. This will give us the x-coordinates of the turning points. To solve for x, we first add 2 to both sides of the equation. Then we divide both sides by 3. Finally, we take the square root of both sides. Remember that the square root of a positive number can be both positive and negative. So, x equals plus or minus the square root of 2 over 3. These are the two x-coordinates where our function turns. We have the x-coordinates. To find the full coordinates of the turning points, we need to find the corresponding y-coordinates by substituting these x values back into the original function f of x. So we'll take the function f of x and substitute our two x-coordinates into it. First, let's use the positive value. X equals the square root of 2 over 3. Substituting this into the function gives us the square root of 2 over 3 cubed, minus 2 times the square root of 2 over 3 plus 3. After simplifying and calculating, this gives us approximately 1911. Next, let's use the negative value, x equals negative the square root of 2 over 3. Substituting this into the function gives us negative the square root of 2 over 3 cubed, minus 2 times negative the square root of 2 over 3 plus 3. This simplifies to approximately 4.089. Therefore, the coordinates of our two turning points are negative the square root of 2 over 3 and 4.089, and positive the square root of 2 over 3 and 1.911. We've completed the first objective for this scene. Let's recap. We successfully found the turning points by first calculating the derivative of the function to represent its slope, then setting that derivative to 0 and solving for x, and finally, substituting those x values back into the original function to find the corresponding y values. Just a quick verification using the memo, our coordinates match perfectly. We are on the right track. Next, in question 3.12, we need to draw up a table of values for our function. Our goal here is to create a table of ordered pairs, x and f of x, which we will use to plot our graph. The instructions specify that x should range from -2 to +2, and x must be an integer. This means our x values will be -2, -1, 0, 1, and 2. We will take each of these integer x values and substitute it into our function f of x equals x cubed minus 2x plus 3 to find the corresponding y value. Let's calculate the values systematically. First, for x equals -2. We substitute it into f of x to get -2 cubed minus 2 times -2 plus 3. This simplifies to -8 plus 4 plus 3, which equals -1. Next, for x equals -1. This gives us -1 cubed minus 2 times -1 plus 3, which is -1 plus 2 plus 3, for a total of 4. For x equals 0, we get 0 cubed minus 2 times 0 plus 3. This simplifies to just 3. For x equals 1, we have 1 cubed minus 2 times 1 plus 3. This is 1 minus 2 plus 3, which gives us 2. Finally, for x equals 2, we substitute it in to get 2 cubed minus 2 times 2 plus 3. This is 8 minus 4 plus 3, which equals 7. We can now populate our table. When x is -2, y is -1. When x is -1, y is 4. When x is 0, y is 3. When x is 1, y is 2. And when x is 2, y is 7. We've now completed Objective 3.12. Let's recap. We successfully created a table of values for our function within the specified domain by substituting integer values for x into the original function. The memo confirms our answers, giving us 2 marks for this part. This table of ordered pairs provides us with key points that will help us draw a neat and accurate graph in the next part. Now for the visual part, question 3.1.3 asks us to draw the graph of f of x and show the turning points. Our goal is to accurately plot the points from our table and connect them to form a smooth curve. Crucially, we must also mark the turning points we found earlier. This will give us a complete picture of the function's behavior. Here's the table of values we just calculated, and our 2 turning points, which I've rounded for plotting convenience to -0.816, 4.089, and +0.816, 1.911. Let's draw our coordinate axes and plot the points. We draw our y-axis and x-axis. From our points, we see y ranges from 1 to 7 and x from 2 to 2. So we can scale our axes accordingly, for example, from 3 to 3 on the x-axis and 2 to 8 on the y-axis to give us plenty of space. First, we'll plot the points from our table. -2, -1, -1, 4, 0, 3, 1, 2, and 2, 7. These are 5 anchor points that will guide our curve. Next, and this is crucial, we plot our 2 turning points. Remember, the first is a local maximum and the second is a local minimum. So the graph must peak at the first point and valley at the second. The rounded values of -0.816 and 4.089 are just to the left of 1 and just above 4. The values of 0.816 and 1.911 are just to the right of 1 and just below 2. Now, we connect these points with a smooth curve. This is a cubic function, so it will have that characteristic S shape. The curve must pass through the plotted points and, most importantly, must show the turn at our calculated turning points. Finally, we should always label our graph clearly. This is the graph of f of x equals x cubed minus 2x plus 3. Let's quickly recap our work for graphing. We successfully used our table of values and calculated turning points to draw a neat graph of the function. The shape is correct, and the turning points are clearly indicated. The memo confirms our graph is correct, earning us another 2 marks. Seeing the graph helps us understand the function's behavior. Notice how it increases, reaches a local maximum at the first turning point, decreases to a local minimum at the second turning point, and then increases again. Now let's tackle question 3.1.4, which introduces us to a powerful numerical method. The question gives us an initial approximation, -1.75, and asks us to use Newton's method twice to find a better approximation of a root for the equation f of x equals 0, correct to 3 decimal figures. Newton's method is an iterative process for finding successively better approximations to the roots of a real-valued function. The core idea is to start with an initial guess, x sub 0. We then find the equation of the tangent line to the function at that point. The next approximation, x sub 1, is where this tangent line intersects the x-axis. We repeat this process, each time getting closer to the actual root. To apply Newton's method, we need two things, the function and its derivative. Thankfully, we already have them. Our function is f of x equals x cubed minus 2x plus 3. And from our previous calculation of turning points, we know the derivative is f prime of x equals 3x squared minus 2. The formula for the next approximation, x sub n plus 1, is the current approximation, x sub n, minus the function evaluated at x sub n, all divided by the derivative evaluated at x sub n. This formula encapsulates the idea of finding the x-intercept of the tangent line. Our starting point, or initial guess, is x sub 0 equals negative 175. We will now apply the formula twice to get a better approximation. Let's perform the first iteration to find our first improved approximation, x sub 1. We start with x sub 0 equals negative 175. First, we evaluate the function at this point. F of negative 1.75 is negative 1.75 cubed minus 2 times negative 1.75 plus 3. This calculates to approximately 1141. Next, we evaluate the derivative. F prime of negative 1.75 is 3 times negative 1.75 squared minus 2. This calculates to approximately 7.18. Now we substitute these values into Newton's formula. X sub 1 equals negative 1.75 minus f of negative 1.75 divided by f prime of negative 1.75, which is negative 175 minus 1.141 divided by 7.188. This gives us our first approximation, x sub 1, of approximately negative 1.909. Notice that negative 1.909 is a larger negative number than negative 1.75. Looking back at our graph, the root is clearly to the left of the turning point, which is at about x equals negative 0.8, and also to the left of negative 1.75. So this approximation is moving in the correct direction. Now we perform the second iteration, using our new approximation x sub 1 as our starting point. Our goal is to find x sub 2. We start with x sub 1 equals negative 1909. Again, we evaluate the function and its derivative at this point. F of negative 1.909 is approximately negative 0.136. Notice that the function value is much closer to 0 this time, which tells us we are getting closer to the root. And f prime of negative 1.909 is approximately 8.929. Substituting these into the formula, we get x sub 2 equals negative 1.909 minus negative 0.136 divided by 8.929. The double negative becomes a positive, so we are adding a small number. The result is approximately negative 1.893. Let's conclude this scene by summarizing our result. After 2 iterations of Newton's method, our better approximation of the root is negative 1.893. This is our final answer for this problem. To recap, we applied the powerful Newton's method to find a more precise root for our cubic equation. We used the function and its derivative to construct an iterative formula, and after 2 steps, we arrived at an accurate approximation. Objective met. Verifying with the memo, our answer is a perfect match. This confirms our application of Newton's method was correct. We now move on to a new problem in question 3.2, which is a classic application of derivatives called an optimization problem. The owner of a dog park has 120 meters of fencing and wants to create a rectangular area with 3 identical pens inside it. Our task is to find the dimensions of the overall rectangle that will give the largest possible total area for the dogs. This means we need to find the maximum possible area, and to do that, we'll use derivatives, just like we did to find the turning points. The process is to first understand the problem, which we can do by drawing a diagram. Then we need to create 2 equations. A constraint equation based on the limited fencing, and an objective equation that describes the area we want to maximize. Finally, We'll use the constraint to rewrite the objective function in terms of a single variable and find its maximum using calculus. The question provides a very helpful diagram. Let's use it to define our variables. Imagine the rectangular area is made up of 3 smaller pens. We need to decide on 2 dimensions that will define this shape. A logical choice is to call the length of the dividing fences x and the width of each small pen y. So let x be the side length of the pen that we can see running vertically in the diagram. The overall length of the entire structure will then be 3 times y. With these variables, we can now write our 2 crucial equations. First, let's write the constraint equation. The total fencing available is 120 meters. The perimeter of the structure is the total length of all the fences. In our diagram, we have 4 vertical fences, each of length x. We also have 2 horizontal fences, top and bottom, each of length 3e. The total perimeter is therefore 4x plus 6i. Since the owner only has 120 meters of fencing, this perimeter must be equal to 120. So our constraint equation is 4x plus 6y equals 120. Second, let's write the objective equation. We want to maximize the total area. The total area of the 3 pens is simply the area of the large outer rectangle. That's its overall length, x, multiplied by its overall width, 3y. So the area, A, equals 3xe. We have our 2 equations. To proceed with calculus, our objective function for area needs to be in terms of a single variable, not 2. So we need to eliminate either x or y from the area equation. Let's use the constraint equation to solve for y in terms of x. Starting with 4x plus 6e equals 120, we can subtract 4x from both sides. Then we divide the entire right side by 6. This gives us y equals 120 minus 4 all over 6. We can simplify this to y equals 20 minus 2/3 x. Now we can substitute this expression for y into our area equation. A equals 3x times the quantity 20 minus 2/3 x. Distributing the 3x, we get a equals 60x minus 2x squared. This is our area function, a of x, and it's now a simple quadratic in terms of x. We have our area function. Now we can use calculus to find its maximum value. Our area function is a of x equals 60x minus 2x squared. To find the maximum, we need to find the critical point where the derivative is 0. So we differentiate a of x with respect to x. Using the power rule, the derivative of 60x is 60, and the derivative of negative 2x squared is negative 4i. So a prime of x equals 60 minus 4i. We set this derivative to 0. 60 minus 4x equals 0. Adding 4x to both sides gives 60 equals 4x. Dividing by 4 gives us x equals 15. This is the x value that will maximize our area. A quick check. The area function ax equals 60x. 2x squared is a parabola opening downwards. Its vertex represents the maximum point. We found the x-coordinate of that vertex is 15. This confirms it's a maximum, not a minimum. We found x, which is one of the dimensions we needed. Now we need to find y and the maximum area itself. We found x equals 15 meters. To find y, we can substitute this back into our expression for y that we found earlier. I equals 20 minus 2/3 of 15. 2/3 of 15 is 10, so y equals 20 minus 10, which is 10 meters. So the dimensions of a single small pen should be 15 meters by 10 meters. The question asks for the dimensions of the overall rectangle. The overall length is x, which is 15 meters. The overall width is 3 times y, which is 3 times 10, or 30 meters. So the dimensions are 15 meters by 30 meters. Finally, we need to find the maximum possible total area. We can use our formula A equals 3e(xy). Substituting our values, we get A equals 3 times 15 times 10, which is 450 square meters. The maximum possible total area is 450 square meters. Let's quickly recap our optimization process. We successfully found the dimensions that maximize the area by following our 5-step optimization strategy. We defined variables, created a constraint equation and an objective function, used the constraint to get the objective in one variable, differentiated it, and found the value that maximized the area. Objective met. The memo confirms that for maximum area, the width is 15 and the length is 30, and the area is 450. Our answers are verified. We've reached the final part of our question, 3.3. This is a related rates problem. The problem states that the radius of a circle is shrinking at a constant rate of 4 centimeters per second. We are asked to find out how fast the circumference of the circle is changing at the exact moment when the radius is 8 centimeters. The key phrase here is rate of change. This tells us we need to use differentiation with respect to time. So, our strategy is to identify the given rate and the rate we need to find. Establish a formula that relates the variables involved. Differentiate that formula with respect to time using the chain rule. And finally, substitute the given values to solve for the unknown rate. This is the standard procedure for any related rates problem. First, let's identify what we know and what we need to find. The problem involves a circle. Let's use r for the radius and c for the circumference. We are told the radius is decreasing at 4 centimeters per second. A decreasing rate is negative, so we write this as dr/et equals -4. We are asked, how fast is the circumference changing at a specific moment? This is the rate we need to find, so our goal is to find dCd. This change is happening at the moment when the radius, r, is exactly 8 centimeters. Now, let's find the formula that relates our variables, r and c. The problem actually gives us a hint. The formula for the circumference of a circle is c equals 2 times pi times r. This single, simple equation is all we need. It directly relates the circumference c to the radius r. We have the formula, so now we differentiate it with respect to time, t. We take the equation c equals 2 pi r and apply the derivative d dt to both sides. The left side is straightforward. The derivative of c with respect to t is dCd. This is the rate we're looking for. So we have dCdt on the left. For the right side, 2 and pi are constants. The derivative of 2 pi r is 2 pi times dr/d. We must include dr/d due to the chain rule, because r is a function of time, t. So the derivative of the right side is 2 pi times dr/d. This gives us our final equation for related rates. d sot t equals 2 pi times dr/d. We have our equation relating the two rates. Now the final step is to substitute the values we know and solve for the unknown rate. We have our rates equation. dCdt equals 2 pi times dr/d. We also know that the rate of change of the radius is -4, and we are interested in the moment when the radius is 8. Let's pause here. Look at our rates equation. dCdt in 2pu. dr/d. Does it depend on the actual value of the radius? No. It only depends on the rate of change of the radius, dr/d. So, while the problem gave us r equals 8, that piece of information isn't actually needed for this particular related rates problem. It's extra information, sometimes called a distractor, but don't let it confuse you. We simply substitute dr/dt equals -4 into our equation. This gives us dCdt equals 2 pi times -4, which simplifies to -8 pi. We can calculate the numerical value of -8 pi. Using pi is approximately 3.114159. This gives us -25.133. The units are centimeters per second. The negative sign confirms that the circumference is decreasing. Let's summarize our findings for this related rates problem. We successfully determined the rate of change of the circumference. We did this by identifying the variables and rates, finding the appropriate formula, differentiating it with respect to time, and then substituting our known rate to get the final answer. Objective met. The memo confirms our final answer of -8 pi centimeters per second. We are completely verified.